So, this is Computer Science 305. Welcome to part 2 of the apparently 2-hour-long experience of Java 2. Anyhow, we're going to be talking about extending and implementing, right? So, we've been talking about all this object-oriented stuff. So now we know that classes can use both extends and implements together. We know they can use extends and they can use implements separately, but now we're going to talk about using them together, right? So you have to think about this. Now we have the ability to not only specialize a more generalized class, right, through extends, but we can also integrate in existing method definitions, method prototypes from some interface as we go along, right? So for every class, the Java language system keeps track of several properties. So these properties include the interfaces implements, methods obliged to define, methods that are defined for it, and fields that are defined for it, right? So all the stuff that we inherit or are forced to implement by definition of claiming that we will implement some interface. So simple cases, right? A method any given method definition affects only C. So if we think about this, right? It's down here. So the method's defined for a class, right? So any method that you define within the class affects only the grouping C. Any field that you define within the class affects only D. And implements, when you claim that, right, affects both A and B because all the interfaces are added to A. And which means that now these are the number of interfaces it implements, right? As well as any methods it's obliged to actually provide an implementation for are added to B. So now we know that. The tricky case for a class is when we talk about extends, because that affects everything, right? Because any interfaces that the class that you've extended, if it was defined abstract and did not implement those interfaces, now you are obliged to implement those as well. So that means that any methods previously not defined are now forced to be defined here, so that affects B. The number of interfaces that the classes above the class you're defining in the inheritance hierarchy implement is added to the interfaces of the current class you're implementing, so that affects A. And then all methods of the base class, right, all the inherited methods are a part of C, and all inherited fields that are defined, and these are only things public or protected, are defined as a part of C and D, right? So D is for fields, C is for methods. So this all becomes really nasty, right? So if we think about this, and we're thinking about the type peekable stack, which extends stack and stack implements work list, we know that peekable stack has the work list interface inherited. It has obligations for add, has more, and remove, which were inherited from the implementations thereof in stack. And then furthermore, and must be able to be called on any object of type peekable stack. Furthermore, it also has so then it has the methods add, has more, remove inherited, plus it defines the method peek, right? And then finally, the field top is inherited, and we did change that to be protected, so that's there now. So all this is a lot of things that we have to understand are available to us in the because we have inheritance through both interfaces and extended classes. So this gets us to the concept of abstract, right? Now I've mentioned this a whole bunch of times, but essentially what we can do is we have to realize that the concept of C, right? C here is the superset of B, as we can see, right? It has all the things that are defined in B, and then anything else that is not a part of one of the interfaces, right? So obligations are only for those things defined as abstract methods that are not yet implemented, or that must be implemented. We just have to be aware of that. So Java ordinarily requires this, right? Classes can get out. So normally we're obliged as a class to implement any methods that we're obliged to, right, to define. Now we can escape this by defining our class to be abstract. Abstract just means that we can never instantiate this, right? So we can't actually create an object of that class. And that means we're not going to be using abstract classes, but abstract classes give us a way to refine our object hierarchies or class hierarchies and gives us places in which we can define common holders of data or behavior, right? So, for example, the graphic class over here actually probably should be defined as an abstract class, right? And then we should then include, and that would give us the capability. We can't actually instantiate graphic, but we can instantiate its subclasses. This leads us to multiple inheritance. So in Java, when it originally was defined back in the 90s, was there because the way they chose to do this was they didn't want to do anything experimental, right? And furthermore, they chose only to provide the things that they knew worked well. Well, back then, there was this problem in C++, and it's called the multiple inheritance problem. It's actually called the diamond problem, which we'll talk about in a minute here. But the problem is let's say we have some class called multifunction down here, right? And this is like, think about a multifunction copying machine that does scanning, copying, printing, and fax. I believe we have one of those in the main office for the computer science department. And some of you may have them at your house, right? Maybe it doesn't implement fax necessarily, but has the other three capabilities. Well, if we were to construct this as an object hierarchy, one simple thought would be, well, what we could do is we could just have these 4 classes, and then we could just inherit from all of them, and then we'd have all of the functionality. Well, this becomes a small problem that we'll talk about. This seems like a reasonable thing to do, except for at least a major problem that we'll talk about. And so Java said we won't be able to do that. We don't want to do this because of this problem. And that problem is called the collision problem, right? So what if we had completely unrelated base classes that we were extending and combining, but unfortunately, two or more of them implement this, define the same method, right? And then we'll call this method transmit. For our example, scanner and fax, right? They transmit data. So the problem here is when we call the multifunction.transmit method, which one actually gets called? And this creates basically a race condition, because essentially what would happen is unless multifunction overrides the inherited definition of transmit, what it's going to do is the system will have to go up to one of the base classes, and whichever one it finds first, whether it's scanner or fax, it will then call that version of transmit. So there's no guarantee that any one implementation of C++ in this case would actually ensure that the right transmit got called. And furthermore, this leads to the diamond problem. Now let's say we have 4 classes, right? A, B, C, and D. A defines some field X, right? Then B has one, and so does C. So D, the question becomes, does D get 2 of them? And even better is, now we have A defines, for example, some, I believe it's called a, not volatile, I can't remember the exact, virtual method, right, in C and C++ and .NET languages. Virtual just means abstract and overridable. So if we have a virtual method defined in A, we'll call it transmit. And then in B, we implement transmit, and in C, we implement transmit. Still, it leads us back to the same question: which one does D call if D does not implement transmit? So this becomes the biggest problem. That's the diamond. This is the problem of the multiple inheritance and diamond problem. We need to have some way around this. So Java said, well, we're just not going to even talk about doing this at all. Instead, what we'll have is any class can extend only one other class if that class has not been defined final. Final is a keyword like abstract on a class. Abstract means I have to, I have to extend that in order to use it. Final says I can no longer extend the class ever, right? It's the last version of it. But Java said we are not going to have this. We'll just have the ability to extend one class only, and then if we need anything else, we have to define it, but we can use interfaces to describe extra capabilities that we may or may not have. This gets a little more wonky in Java 8, which allows default implementation of methods inside interfaces. And then in Java 9, we have the capability for, I believe, You can have fields inside of interfaces now, and Java 10 is adding something else to it. But it's going to be interesting. So we can solve the diamond problem, right? And this is how we did with, and basically this is alluding to how we did with Java, right? So you can have multiple inheritance, but you must have mechanisms for handling this, right? It's not really all that tricky, and but the question really comes down to what is the additional power of being able to have multiple inheritance worth the additional language complexity that would need to be there? And the interesting thing is, as I've been alluding to, Java's designers did not think it was. So we don't have multiple inheritance. It doesn't and the interesting thing here is, in reality, if we think about real life or physical objects or things that exist in the real world, right? Because we have to go back to philosophy to understand object orientation and its notion called ontology. And ontology is the study of that which exists, but we can construct basically these hierarchies of all things, describing the hierarchy of all things that exist, and sort of base abstract notions down to what we actually see in the real world. And we can realize that most things are not single inheritance relationships. They are multiple inheritance constructs, right? But is it really worth being able to model it that way, or can we relax and have the more simplified modeling that we have in things like Java? Right. So one of the benefits of multiple inheritance is that a class can have several unrelated types, like copier and fax, but instead we do this in Java using interfaces, right? And then we make a claim like, we can create the fax, copier, scanner, and printer interfaces that we then implement those methods inside of our actual class. The other way we can do this is through composition. Now this gets in, I guess I am going to be talking about composition, favoring composition over inheritance. So inheritance is great if you have, and this is one of the ways around the multiple inheritance problem, right? Inheritance is a really good way of describing a hierarchy of very interrelated things where you have the is-a relationship between things. And so that's saying that because it's polymorphism, any subclass is a superclass, right? It is one of the things. It's equivalent to being the same as its superclass. It just has more functionality. Now the problem here is that relationship doesn't really translate well to everything, right? And actually, a multifunction copier is not all the different things. It contains all those things, right? It's a printer. It contains the capability to be a printer. It contains the capability to be a copier. It contains the capability to be a scanner. It contains the capability to be a fax. So it has of all these things. And this is composition. More often than not, composition is the better way of approaching things. And so instead what we want to do is we want to have the ability, we use composition basically where we have fields relating us to those different things. And then we contain those inside of the class that we want, like multifunction here. And then we define methods that we then call, that are delegators. They delegate the processing to those contained items. So we call copy on multifunction, and then what ends up happening is that we're really calling the copier's copy function. Same with scanner. We call transmit on scanner rather than when we call transmit scanned on multifunction. Same with fax. We call send fax. That really is calling transmit on the fax component. And so this is a better way of looking at this, and it's a well-known object-oriented design paradigm and design principle. So finally, Java. Java had a severe weakness that was identified back in, I think it was Java 1.4.2, if I recall. And what it was is that essentially, if we were to create a stack of things beyond, for example, strings, right? We create this stack. It's a really great stack. It's really good, but it only can work with strings. And because Java is a very, we'll say, statically typed language, a very strongly typed language, it has certain issues with what we can do or can't do with it. It can't be reused. So, like, if we create an object of type stack, we can't use it for anything but strings. We can't adjust that at runtime. It's just for strings. It can never be for anything else. What we'd like to have is a capability where we could adjust what kind of types could be used. And this led us to generics, right? So in ML, we had special type. We had special type variables, right? The apostrophe A, as we see here, right? That's indicating that it can be a polytype. It can be whatever, basically. Ada and C++ have similar concepts. But back in the old days, prior to Java 1.4.2, it did not have the capabilities for what we call generics now. In C++, we call these templated classes. And so, before, what we had to do is essentially, if we need to use any very polymorphic construct where we could just use any type, we ended up having to use a base type of object, right? So essentially, our stack would look. Let's take a look here if I can open up stack. Instead of having a string, right? Oh, sorry, node. Instead of having a string for our data, it would just be object, and then we'd everything would be object, and you'd have to do all these nasty instance of casting, and then cast all of your data all the time. It was, I remember programming that way. It was very disgusting. So essentially, we'd be doing exactly what I'm doing right now. We have our object data. We have node link, right? And we have to change the constructor to be object, and maybe adjust everything. Instead of saying string, we say object. And so now we have, I have to go object. Good lord. Okay, there we go. So now everything's changed to object, and we have to go back into our work list, and we have to adjust that to be object. It's this really nasty experience, right? And then our remove has to be object, and then we go back into node. What did I break here? Oh, down here. Oh, yes. I override. What do I override? Oh, that would be toString. It's a bad problem of using cut and paste. So anyway, so that's fixed, right? Now we go back to our stack, and we look at this, and it says, oh, well, it implements work list. Unfortunately, we have to make this change to be object, and then we have to change remove to be object as well. Right? So now we fixed everything there. Looks good. And then we have to change peekable stack to now be object, right? So now we can deal with this. The only problem here is if we go back into our driver class, and now we go ahead and run that. Well, it probably will actually work. So it does work because we expect string for everything, right? But if we need to do any other type of operation here, for example, if we want, we could actually say, so W, but the beauty here is now we can actually add in things like, oh, let's see, w.add 1, right? So 1 is a base type integer, but it will be autoboxed to be type java.lang.integer with a capital I. And so if we go ahead and run this, right, it does say 1, the cut worm forgives, because we only did 3 of them. And so, but now we can store whatever we want in there. We could actually store another stack inside of it. We could do literally whatever we want. Now that's really nice and everything, except for if I need to manipulate this, right? So now if I was to go down, if I want to look at this, I can say w.peek, right? Oh, sorry, that's not going to work. I need a peekable stack. So let's go down to here, where I actually have one. So S2, right? So now if I say S2.peek, I get an object, right? So now I have an object type, which is not really that useful because now I have to do things like if I want to do string concatenation on this, I can't do it straight up. Well, actually I can, but trying to think of anything else I could do. Anyway, essentially the problem becomes is I don't have any of the normal operations I would like. So if I say s plus 1, it gives me an error, right? The operator plus cannot be applied to object in int. So I'd have to call the .toString method and hope that that works, which apparently it's not a statement. So then I'd have to say s equals, and that would do enough, right? But the problem here is that you have to start doing a lot of extra business that we didn't want to do. So now, the other problem here is there's no type checking, right? There's no when we start dealing with object by itself, we end up having no actual compile time type checking on our element types, right? Everything is of type object in Java. So we can do whatever we want, which is probably not a good thing. And in the case that maybe we do have an error, right? Which in this case, as we see here, we're actually constructing we're adding S1 back to itself, which is probably not something we really ever want to do because that's going to cause all sorts of weird issues that I don't even want to try to fathom how that would work. So this is probably not something that we really want to be messing with, but we would probably not be able to detect this because this would not throw a straight up compile time error. So we'd have to figure out what we can do now. And as I was saying before, if we want to recover the actual type of a stacked object, we'd have to use an explicit type cast, right? So as it says here, right, if we said s1 dot add, so we say s1 dot add hello, if I can spell, and we want to actually get that back, we say string s equals, and then we have to cast it, right? And let's call this str. Now the actual problem here is this can actually lead to potential errors because we don't actually know if this cast is legal. We know it is because we added a string and that is the only thing we got back. But if you have lots of different operations happening, you may end up getting back something that's not actually a string. In reality, all things in Java could be coerced to string, but that's not really the point. Furthermore, now they make this argument here that primitive types must first be stored in object before being stacked. As I showed you earlier, that's not true. In reality, it is. This really does have to happen, but what's really going to happen is it'll use the Java, since Java 5 or 1.5, depending on how you want to look at it. Java has been using auto-boxing and auto-unboxing, so it'll wrap automatically and unwrap automatically primitive types. So boolean, char, int, long, double, etc. It automatically wraps and unwraps those for us, so we don't have to worry about it necessarily. And this happened because of generics. So when generics occurred, they started doing this so that it would be a little bit easier. So now, in Java, since 2004, Java 1.4.2, we've had this capability to use true generics. So now, this gives us the ability to parameterize polymorphic classes, interfaces, methods, and constructors with type variables that we'll then use. Then at runtime will be reduced down to a specific type. So now this gives us the ability to use any type. And then furthermore, there's wildcards and all these other things. So now we can actually create and modify, go back and modify all of our instances, right? So we have work lists. Now we'll add a type variable. So in the diamond bracket, we add the type, in this case, t, right? And so now this is just a placeholder for any type. And then what we need to do is anywhere that we had object before, we then use t, right? And so now this gives us the ability to actually utilize this. And so work list now can hold anything, any type. The secret here is, though, that once you've reduced it down to a limited hierarchy, right? So if we choose string, you can't extend string. There's no extensions to string. It's a final class. So once we have a string, we can only put strings in there. But on the other hand, if we chose to use number, which is the superclass of the object versions of the primitive numeric types, as well as other ones such as big decimal, big integer, and a few other things, we can actually use that, and then we can use all sorts of different things in there, as long as they are a subclass of type number. So we'll get a little bit more into that. If we were to go through, then we have to go modify node, right? So in node, we replace object with t, and then we put in diamond brackets t, and now we have a genericized node class. Right now it can take in any type as long as it falls in line with t, right? And then our get link should also return a type node t. Now we have that. Now we just need to go and same with this. All right, now we're good to go. Once we have that good finished, now we can go modify stack and peekable stack. So we'll replace object with type t. And I think we need to fix node to be t. Now the only other problem here is, and I actually have to fix this, so then we have to say public class stack takes in a type t, implements worklist type t, and so now we're good to go. The only problem that we have is in this construction of the type node here, right? It's showing me I have an unchecked assignment from a generic node. So node by itself, when we don't put a parameterized the diamond bracket here, it's going to assume node object, right? So we have to modify this, and so you can use a new node and then put type t in the bracket. But if you're actually doing this, it's easier to just use the diamond bracket by itself, and it will infer the type that we need based on the initial definition right here. So now we're good to go. We fixed that, and we just need to fix peekable stack to return type t from peek, and make sure this is of type t and stack type t. Okay, good to go. All right, now we go back into our driver and say we new stack, and we say that, and we'll make this type, let's say string. And that's going to cut. Now we start seeing that we're getting errors, right? So obviously integer is not of type string, so we'll destroy that for now. And we come down here to this peekable stack, which we'll put the diamond operator on there, and make that of type t. String. And do the same thing for this, and make that like that. All right, looks good. Everything else. This will come out as a string, and we will have no problem there. Everything looks pretty good. If we go ahead and run that, we should see what we expected. All right, it looks good. So this is the basic construct of generics. It just gives us the capability to do parameterizable typing for actual classes that we're using. Now the interesting thing is this is very basic. We haven't even gotten into where you can use this for methods, anything like that. It's just, and if you really are interested in using generics, I would definitely go and take a look at other things, and maybe a tutorial on generics. Note, as I mentioned before, when we use these, right, we can have coercions, right? So if we had a second one, well, I'm not going to implement that, but for the stack of integer, right, we can say s2.add1, which is a primitive int literal, which will automatically be auto-boxed to a type of integer from java.lang, and then when we need to manipulate it or remove it, right, it will be auto-unboxed back down to a primitive as necessary. So bear that in mind. And that, as it says here, was also added in 2004. That was added as a part of the generics package to Java 1.5. Anyway, you have a great day, and I'll talk to you all later in class. Have a good one.